All right, so I gave students a couple minutes to start 3.25. Context here is using a person's height to predict their weight. Students were asked to complete this particular problem. Now, I don't care if you went with weak or moderate. I would take either one of those. The reason I would take either one is because you weren't actually given the correlation coefficient. So I would not expect any of you to be able to look at this and know what the R value is. That would be kind of crazy. If you did take the time to type that data into an analysis tool, the correlation comes out to be 0.628. So if you had that, everyone should be saying weak. But because it's visual, again, if you said moderate, no problem. I wouldn't want you to say strong. I think the data is too spread out to argue strong, especially with the existence of this outlier. I mean, in general, this is the pattern the data seems to follow. You've got this point here that's clearly going against the general pattern. Okay? And that is, by the way, the outlier that I mentioned in my write-up. Okay? So weak, so you want to make sure you have form, direction, strength. That's linear, positive, weak, or again, moderate. When we say context, what we really are referring to is tell me what you mean by positive. So in general, if you are taller, I expect you to weigh more. And for those of you who still haven't gotten on board with the need for non-deterministic language, it would be very easy for me to find an example of a student pair where the taller person weighs less. It's very easy to find micro examples buried within the data where the taller person weighs less. The taller person weighs less. Okay, so the macro pattern is, in general, the taller you are, the heavier you are. Okay, but there are plenty of examples within that that would go against that pattern. This is hence the need for non-deterministic language. Questions on A? Yes. All right. Now, the reason I wanted to design B is because if I ask you all to sketch a line of best fit, so if I told you all, look at the graph and sketch the line of best fit, I would hope nobody would do anything like that. That would be kind of absurd, okay? But many of you would give me lines kind of in this general area. Does that make sense? So we would all kind of subjectively disagree about what the exact line should look like. However, I wanted to present to you that if you're ever given the equation, well, then there is an objective process you can follow so that we all essentially get the exact same line. Hopefully you remember from geometry, how many points do you need to build a line? 2. So that's all you need. Now, I did you a favor on this question. It says, given the equation, the line of best fit is this. So we got predicted weight is negative 74.25 plus 3.26 times the height. Sketch this model by plotting the expected weight of a 5'0", that's a 60-inch person, and a 6'8", that's an 80-inch person. The favor that I've done for you is I've handed you the concept of get 2 points. If you want to sketch a line, get 2 points. You can't expect me to do that same thing for you on future quizzes and tests, and certainly not on the AP exam. If you are given a linear model and then you are asked to sketch that model, they're not asking you to give a best guess of where you think the line should be. They're telling you, show us where the line is. Give me the line. Okay? And the way you do that is get points that you know are on the line. Okay? So if you plug in 60 to the equation, you find that we would expect a 60-inch tall person to weigh 121 pounds. If you plug in 80, you find that we would expect an 80-inch person to weigh 186 pounds. I'm going to zoom in on that just so it's a little bit easier for folks to copy. Bear with me. Where is it? There it is. All right. After you copy that, take a moment to try to plot those 2 points and then draw the line that connects them. Okay? Go. All right, let me zoom back out to show you what I did here. So again, we expected a 60-inch tall person to weigh about 121 pounds. So I basically put that on our vertical axis and then plotted a point just above 120, like barely above 120. And then we expected an 80-inch person to weigh 186 pounds. So again, that was my best approximation of where that point might be. And then to draw the line, I connected the dots. Okay, so this is an objective process that we could all follow that would now more or less get us all the same line. I mean, yes, even when you plot the points, there'd be tiny little variations, but we basically all get the same line. Now, if I hadn't gone out of my way to tell you use a 60-inch person and an 80-inch person, and I instead just in general said, here's the equation, sketch it, I don't care which points you want. If you wanted to use a 64-inch tall person who's 5'4" and a 6'4" person who's 76 inches tall, go for it. I don't care what points you choose. In fact, if you graph those 2 points, not surprisingly, those are just 2 more points that are also on the same line. Okay? So again, if you have access to the equation and you're asked to sketch the line, not a best guess. It's a get me 2 points you know are on the line and connect them. That's how you draw a line. Okay? Question. All right, so on this page, we practice just can you describe an association, form, direction, strength, unusual features, context, non-deterministic language, all those good ingredients. This was me trying to show you an objective process for graphing a line. Now we're going to move to kind of breaking down the parts of linear analysis. One is interpreting the slope in context. Now, I want to be clear. We're given the equation, and you know what? Let me jump back for a moment. Yes, that's what I wanted to talk about. So don't feel like you need to go back here. I just wanted to remind you that when we look at a printout like this, what I told you all is that there are key pieces of information that need to pop out at you. Okay, so remember, when we're talking about the equation for a line, coefficient is just a fancy word for numbers in an equation. And a linear model needs 2 numbers, the y-intercept and the slope. That's it. Now, the y-intercept is a coefficient, a number that is by itself. We call that a constant. The other coefficient, which apparently is attached to the variable year for this problem, would be your slope. So I want you to be able to look at this printout and instantly know what's the y-intercept, what's the slope. Okay? Now, in the situation we're dealing with here, when I ask you all to interpret the slope, you can't even do that unless you're able to look at the equation that was given to you and know the y-intercept is negative 74.25 and the slope is 3.26. Now, remember, slope is y units per x unit. That's what slope is. In this particular case, we are trying to predict weight. That is our y unit, pounds. We're using height, inches, to make that prediction. So our slope literally references pounds per inch. That's what you need to tell me. You better use the number 3.26. If I ask you to explain the slope, well, then you got to use the slope. Okay, and don't forget your non-deterministic language. I expect a person to weigh 3.26 pounds more per inch in height. After you're done copying that, try to take a moment to appreciate why the red is wrong. So absolutely, the red is wrong because it doesn't say anything about how much height increased by. When you just tell me I expect weight to go up 3.26 pounds, it's like, okay, but when do you expect that to happen? If I grow 4 inches, if I grow 10 inches, like when are you expecting that to happen? The word per automatically means 1. So 3.26 pounds per inch. So 1 inch, 1 inch, 1 inch, I expect you to gain 3.26 pounds. And by the way, I think I said this yesterday, use whatever multiple you want. Like if you wanted to multiply the number by 10 and say, I expect a person to weigh 32.6 pounds more when they are 10 inches taller, fine, you're saying the same thing. Okay? Questions? All right, other than interpreting slope, you also need to know how to interpret the y-intercept. Does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. If not, explain why. Real quick, common misconception I want to address before I keep pushing forward. I will have students that will look at this picture and tell me this, meaning this, is your y-intercept. You're totally wrong. I get that with the way this is graphed, it looks like it hits the y-axis. It doesn't, okay? Remember, the y-intercept only occurs on the y-axis, which requires an x value of 0. This is not the y-intercept because it occurs at an x value of 60, not 0. So if you wanted to visualize the y-intercept, what you'd have to do is track this axis all the way back to 50, 40, 30, 20, 10, 0, which is off the board several feet. And then you'd have to track the line down, 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 down here off the board somewhere. Does that make sense? The y-intercept is off the board down here to the left somewhere. And apparently, it's hitting somewhere down at negative 74. That's where the y-intercept is. So you can't even address this question unless you understand that the point 0, negative 74.25 is your y-intercept. Now, in context, that would refer to a person who is 0 inches tall and weighs 74.25 pounds, which neither of those makes any sense. So I would say no, because a person cannot be 0 inches tall, nor can a person weigh negative 74 pounds. All right, moving on. Please ignore that random comment. All right, given R is 0.628, interpret R squared in context. So, of course, this might be one of the things you need a calculator for today. But I want to be clear that, and this is a little weird, R is what is used to describe the strength of a relationship. But for whatever reason, statisticians are attached to using R squared when trying to describe how accurate or reliable a model is. Okay, so R is for discussing strength. R squared is for discussing reliability. Now, the whole idea here is we are trying to predict variations in weight. People's weights go up and down and up and down, and we're trying to kind of capture that variability. Now, we do that by controlling height. That is not something that is variability we're not controlling. Like, that's the explanatory variable. I can plug whatever I want into the model. I can plug in 50 inches or 60 inches or 67 inches. I can do whatever I want. I control the variability of the height. But I use that to try to capture variability in the weight. That is what R squared kind of talks about. What percent of that variability in the unknown variable of weight are you able to capture? So the way I would say this is variation in height, which is again the thing I control, because I can choose whatever I want to plug into the equation, explains about 39.4% of variation in weight. Now, what I tried to stress in an earlier lecture is I don't really care how you want to phrase this. In fact, I present 3 other ways because in my experience, this is the thing that kids struggle with the most in terms of writing clearly on. Like when I give you all the chapter 3 test, historically, if I give you a question that says explain R squared in context, that seems to be the thing that most people trip up on. So I'm trying to show you a bunch of different ways that you'll get full credit. But what I want you to notice is that the common link is they all refer to variation in weight, because that's the whole point of this model. The model is used to try to predict weight. Okay? Questions? All right, last thing I'm going to do before I ask you all to do some stuff yourselves. It says, how does the 5'9" student in this group compare to their expected weight? Okay. Now, I don't know if you caught it, but next to this graph on the previous page, we were given a table of values. Okay. 5'9" is 69 inches. There's only one person on this list that was 69 inches tall. They weighed 140 pounds. So that is the person we're focusing on here. And what we're being asked is how does this person compare to their expected weight? Okay. Now, if you wanted to, you could focus on this point. That is the point we're referring to. That is the person who is 69 inches tall, weighs 140 pounds. Now, I have a question that I don't want anyone to audibly respond to, meaning be quiet. Just let everybody process this question themselves. Is this person lighter or heavier than expected? Again, please don't say anything out loud. I want everyone to have their own chance to process this. Does this person, that point at 69, 140, is that a person who weighs less than what we thought they would or more than what we thought they would? Okay, hopefully you were thinking less. The line is what makes a prediction. The line represents this is where we think you would be. So according to the line, if you are 69 inches tall, we thought you would be up there. Does that make sense? So they weigh 140. We thought they would weigh, it looks like maybe a little bit more than 150. So they weigh about 10 pounds less than what we expected. That is what we refer to as a residual. Okay? So that distance, which is apparently 10.69 pounds, so I said it was about 10. So apparently, the way this question is going to end is we are going to say, this person weighs 10.69 pounds less than expected. Like, that's going to be the final sentence. Okay? The question is, how do we get there? So, of course, you're going to need to know their height is 69, but that's the number that you plug into the equation. That is where you get your expected weight. So, according to this linear model, we would have expected this person to weigh 150.69 pounds. Now, we have this thing called a residual, which is always the difference between your actual number and what we thought. And it goes in that order always. Okay, I like the abbreviation I like to remember is RAP. Residual is actual minus predicted. RAP. Residual, actual, predicted. In this case, this person's actual weight is 140. What their predicted weight is 150.69. And when you subtract them, you get a negative difference. By the way, our z-scores work the exact same way. If you wanted a z-score for this person, 140, you start with 140 and then you subtract the mean. It's what is your actual weight? Now let me subtract the mean, because the mean is kind of what I thought anyone would be, to get that differential. Okay? Now, by the way, if you make the mistake, and this is a super common mistake, if you make the mistake of subtracting in the wrong direction, so you do 150.69 minus 140, you get a residual of 10.69. I would suggest that is something you can realize doesn't make any sense by just thinking about the picture. I asked you all, look at the picture and tell me, is this person less than expected or more than expected? Well, they're under the line. So they are less than expected, which means the residual better be negative. Okay? So this person is 10.69 pounds under their expected weight. Now, before you turn the page, I have one other thing I just want to talk. We're done with the problem. So technically speaking, you could turn the page, but let me say one other quick thing. A common wrong phrase that somebody will say in this final sentence, and I want to preface this by saying this is not a picky thing. If your reaction to what I'm about to say is, oh, geez, that's really picky, you have a serious misconception going on. So I need you to kind of pause and really process what I'm saying to you. If you say this person is 10.69 pounds under the average weight, that is a completely different statement, and you're wrong. Okay? There's a massive difference between claiming a under expected versus under the average. Let me justify that real quick. If you add up all these weights and calculate the average comes out to 144.8, whatever. So this is a person who weighs 4.8 pounds below average. That is a completely different thing than below expected. Does that make sense? So if you make the mistake of saying this person is 10.69 pounds below average, you are wrong. Okay? In fact, and this to me is kind of a cool thing to look at, okay, this line, let that line represent the average weight right here. Anybody that is under this line is below average. Does that make sense? But anybody that is above this line is above expected. Does that make sense? So if you, in fact, let me shade the other direction. Let me shade above in both. Okay, just so it's a little bit easier to follow. If you are anywhere in here, you are above average. If you are anywhere in here, you are above expected. Does that make sense? So you can be both. If you're here, that is somebody that is both above the average weight, and they are also heavier than we thought they would be. They are above expected. They're both. But if I take somebody that's right in here, well, now you're talking about somebody that's above the average. They're more than 144 pounds, but they're under the line, so they're still less than what we thought they would be. Does that make sense? And this person, that's kind of, it's hard to see, but you know, I got a couple points trapped on the other end between the lines. Those are points, those are people that represent below average. You are less than the average person, yet you are more than what the line thought you would be. You're above expected, but you're below average. So those are two completely different statements. And of course, you can be below both. If you're anywhere down in here, not only are you less than expected, you're also less than average. Okay? All right, at this point in the class, I'm giving students some time to work ahead of me on 3.27, and then when the timer's up, we'll go through this problem. All right, so I gave students time to work ahead. As you all working, I revealed the answer to part A. First of all, everyone should have said weak. The correlations are both reported to you. Remember, 0.5 is weak, 0.7 is moderate, 0.9 is strong. Okay. In terms of context, both graphs clearly reveal that in general, people that are taller tend to weigh more. Okay. And rather than trying to mention 70,000 outliers, what I noticed was in both displays, you sort of have this funneling effect where the data gets further and further apart as you go above. out to higher heights. Okay, I did. Now, down at the bottom, the thing that I would hope everyone noticed is that these graphs are communicating that men on average are both taller and heavier. Now, the way I tried to come up with that decision was I estimated the center of mass of the data sets. Okay, so please don't think those are correct points. Those are literally just my visual attempt to approximate the center of mass. But you can see that the height for the men is 72 over 66. The weight for the men is 290 over 150. Okay? Or I realize now that should say 190, not 290. That's a typo. But still, 190 is more than 150. Okay? Now, in terms of variation, this is the thing that I doubt everyone would have noticed, but here's my attempt to compare variation. I imagined a box that encapsulates all of the men, all of the women. Now, I realize you all don't have the fancy Promethean boards, you can't really do this, but let me kind of explain the thought process. If you notice, the height of these boxes is basically the same. What that's telling you is the distance between the lightest woman and the heaviest woman is basically the same as the distance between the lightest man and the heaviest man. Does that make sense? Okay, so that was sort of the thrust I used to try to make the claim that in terms of weight, they're about similar. Now, that was a similarity, which is why it's in green, because the question doesn't say anything about mentioning similarity. So for those who love to write me essays, anything you write here about how they're similar, I'm going to ignore completely unless you state something that's outright false. If you state something that is outright false, it can hurt you. So answer the question and move on. Don't prove to me what you know by just putting anything on the page. Okay? Now, if you then instead look at the variability in height, so the horizontal distance, you'll notice that the male distribution reaches a wider range of heights. Okay? So that was the other thing. I didn't just compare centers. That's what that first sentence is. This is a comparison of center. I also compared spread. And I said male heights vary more. Okay? That is what this graph is communicating to you. Not only are men in general taller and heavier, but also their heights tend to vary more. Okay? Now, these graphs would communicate weights not so much, but I already mentioned that. Questions? Yes. All right, go ahead and turn. Now, all three of these questions are a very similar flavor. They're all basically saying, can you do this? Can you do this? Can you do this? Now, I'll ruin a little bit here. The answer is no in every single case. In every single case, you're being told to do something that, probably shouldn't really do or can't really trust. But every single question has a completely different reason why. First one talks about using a linear model where you're slamming all of the data together. That makes absolutely no sense. We just said there's noticeable differences between men and women. So if you want to make a prediction for a student that's 60 inches tall, tell me if they're a man or a woman so I know which model to use. Okay? It makes no sense to use one model for everybody when you just highlighted that they're different. Okay? So I said, no, there are clear differences between the men and the women. Okay, so I would not use a model for all data. That would be like taking all the points and just slamming them into one big scatter plot. Okay. Now, for the next one, this is the only one that would require a calculator because, yes, you would need to find R squared. It is appropriate to use the female graph to make a prediction about a 60-inch female. It's appropriate. But would you trust the accuracy of that prediction? I argue no, because the model only accounts for 33.8% of the variability. By the way, I have since changed this question. I literally changed it this morning. I wanted the question to be a little more clear. So what I reworded it to say was, would a linear model for the women account for at least 50% of the variability seen in weight? That's a way more straightforward question. And then the answer is yes, or excuse me, no, because it only accounts for 33.8%. Much more straightforward question. Okay, but again, R squared is the statistic we use when we're trying to decide how reliable is this model. Okay. Now, the last question talks about a 60-inch male. Every single one of you should be able to tell me in one word that starts with letter E why you should not be using this model to talk about a 60-inch male. not empty. Extrapolation. Your shortest male in this data set is 63 inches tall. That means anything lower than that is considered an extrapolation. So would I trust that prediction? Not necessarily, because this would be extrapolation. My shortest male is 63 inches. Okay, so that's a whole extra layer of I don't know what the heck I'm talking about if you're going to use that model to make that kind of prediction. Okay. All right, with that, we are done. Thank you for watching. Have a good one.